2, 1. Alright, let's go. We've got a Math 2070 online video. And today we're going to revisit linearly independent sets in the context of vector spaces, which will lead us to talking about bases. Ooh, for vector spaces. Fun stuff. Oh, hey, let's go ahead and revisit linear independence. So, alright, recall that linear independence formally is the requirement that if you have a list of vectors, v1 to vn, if you can create the trivial linear combination, so in other words, if you can scale and add up your vectors, and you get the additive identity of your vector space, then the only way you could have done this was if only the scalars that you used were 0. So again, in the context of Euclidean space, we saw linear independence was asking that the columns of a matrix are linearly independent precisely when a times x equaling 0. The homogeneous system only has the trivial solution. And it's right, again, a matrix multiplication is scaling and adding the columns. So, alright, just recontextualizing all of that good stuff here in the language of vector spaces. So, right, this is precisely how we saw linear independence behaving for Euclidean space, for Rn. But there are other vector spaces that we can interact with and play, and then ask about the linear independence. And one that we're going to frequently visit throughout the remainder of the semester is the set of polynomials. And it's worth noting that the polynomials, the constant function 1, t squared, all the way up to t to the n, these are linearly independent, because if we were to scale and add them and get 0, then the coefficients must all equal 0. Right, and why is that true? Well, that has to be true because if it wasn't, if we had non-zero scalars, then we have a non-zero polynomial, but if it's constantly equal to 0, that means this polynomial has infinitely many roots. Every real number would be a root of that polynomial, and that can't happen. We know polynomials have at most finitely many roots. In fact, we know the roots are bounded above by the highest power that we see in the polynomial. Alright, nice. So this little trick is pretty good, because not only does it give us when polynomials are linearly independent, we can actually use it to verify when other collections of polynomials are linearly independent. So for example, if I have this collection right here, well, if I want to know if these are linearly independent or not, following the definition, I scale and add them up, set it equal to 0. And then the maneuver here is to collect all of the like terms. We'll get all of our constant terms together. Right there. All of our terms that involve the variable t, all of the t squared terms, and all of the t cubed terms, so on and so forth. Alright, now we have a polynomial that is identically equal to 0. The only way that could happen is if all of the coefficients are 0, as we just argued. And then that gives us, hey, a system of linear equations to solve for. And this one's pretty quick, hopefully, to see that, yeah, all of them have to equal 0. This here tells me, for example, that C2 has to be C3, and plugging it into this one, you're right, immediately tells me that C2 and C3 are both equal to 0. Right, so however you want to solve this, this would tell you that C2 is 0 or C3 is 0, which would then guarantee that everything else zeroes out. Oh, I don't know if you can hear that, but cats are fighting in the background. Alright, now this is quite a nice argument, right? But note, it can be a little computationally involved. And if you take out your spectacles and look close enough at the vectors involved, the polynomials involved, I have a 1 and a 2. 1 and a 2. Right, the coefficients on the constants. Right, for the t terms, I have a 1 and a negative 1. 1 and a negative 1. Right, and if I really pay attention to this, it kind of looks a lot like a 4x2 matrix. Yeah, there might be some deep connection, like almost that these are really just elements of Rn in disguise. Ooh, well, we got to make that a little bit more formal, so let's talk about what a basis for vector space is. Alright, so a collection of vectors, which we will conglomerate together with the set notation using the curly braces. B is a basis if it does two things. It spans, and it's linearly independent. Right, so again, span means that every element of the vector space is a linear combo of those vectors, and linear independence we've just described. So, the polynomials, 1, t, t squared up to t to the n is a basis for the polynomials of degree less than or equal to n, because every such polynomial is just literally a linear combo of those things. That's what this set is. And we just verify that this is a linearly independent set, so hey, we get a fun little basis. Let's turn our attention to what is that? I don't know. At least it's a spelling mistake. It isn't a math mistake. That's better. Anyway, so here we see we've got a basis for the set of polynomials, and note something, we have n plus 1 here, even though this is the polynomials of degree n because of the constant term adding an extra. More cat nonsense, whenever you can hear that. Alright, now, as we've kind of already let slip, it really seems like these polynomials are really just vectors in Rn in disguise, so let's go back to Rn and look at bases there. All right. So, some obvious examples we've already encountered are the standard basis elements, the E1, the E2, the E3. Right. And it's not too hard to verify, as we already know, this collection does span, and it's clearly linearly independent. If you scale and add these up and set them equal to 0, then the coefficients immediately have to equal 0. That's just the way breaking things up using these vectors works, because there's only 1 in one entry and zeros elsewhere. Okay. However, while great and as useful as this basis is, there are occasions, there is reason to use other bases, and we'll see throughout the semester the sort of situations where I need a different basis. So it'd be good to have a general blueprint of how to create bases for Rn. Right, and so note something, this tells us bases are not a unique idea. There could be multiple bases for a given vector space. Right, and here to show that we can easily construct bases for Rn, quite easily, if you have the columns of an invertible n by n matrix, note that in order to be an invertible matrix, the columns must span, and the columns must be linearly independent. So literally, if I have an invertible matrix, I have a basis, and vice versa. If I have a basis, I can create an invertible matrix. Nice. So, for example, here are two vectors. Set up the matrix by smashing them together. This has to be invertible. Note its determinant is 1, so it's non-zero. So it's got to be a basis. Hey, there you go. Easily constructing bases for Euclidean space. You just got to find an invertible matrix, and you're good to go. Right, and good thing we've got that big-ass theorem that's going to tell us how to get invertible matrices. To quote a comment, the worst alphabet soup I've ever seen in a math class. Shout out to whoever wrote that. Alright. Sweet. Alright, now that we have this notion of basis, and we're able to compute bases by finding an invertible matrix, let's talk about some other bases that we can find in terms of matrices. So as we've kind of already mentioned, every matrix comes along with some fundamental subspaces. Some subspaces that are quite important for a variety of reasons. And it's going to be very nice to have bases for these subspaces. And in particular, let's talk about finding bases for the null space, column space, and row space of our matrices. Okay. So consider the following matrix. The augmented matrix for x equals 0 is the following. So I take the matrix, I reft it. That gives me the elements of my null space. They have to satisfy those, so any element of the null space has to satisfy these. And let's be a little careful that there is a phantom x4 going on here, because there's a column of zeros. So every x in the null space is of this form here. Now note x1 has to be 6x2. X3 has to be 0, but X2 and X4 are free because, again, they're not a pivot column. 1 and 3 are pivot columns. Alright, and that lets me pull apart the vectors as follows. And in particular, if you look at this, you see that, well, the null space is spanned by these, and guaranteed, because of the reducer echelon form, these are going to be linearly independent. Right, any other row operations you perform to this, so for example, if these were not linearly independent, well then we'd be able to do some row operations and get it into a more reduced form, but we already had it in its reduced form. Right, so if you want to find the basis for your null space, it's literally just solve for x equals 0. Nothing new or fancy or anything, just recontextualizing something we've already done. So, solving for getting a basis for your null space, pretty straightforward, something we already did. right? So we just got a new way of looking at it. All right, let's talk about finding bases for column spaces, though. Right, so first note, recall what the column space is. It's the span of the columns. So if you've got a list of elements of your m by n matrix, then we can get the columns and look at the span of that. However, we know the columns may not be linearly independent, so this is technically not going to be a basis. Even though it does span, it may not be linearly independent. The good news is, though, that the pivot columns do have to be linearly independent, and will have to span the column space. And the best way to see why this is true is with an example. So consider this 3x3 matrix. There's its reduced row echelon form. Note the pivot columns, column 1 and column 2 are the pivot, column 3 is not. But note something. Hey, column 3 is a linear combo of column 1 and 2. And that exact linear combo, if we bring it back to the first column, holds true. Right, so you can verify 2 plus 3 times 7 is 23. 2 times 2 plus 3 times 4 is 16. Negative 2 plus 3 times negative 2 gives me negative 8. Right, and so this will actually always happen. And there's good reason for this, or sort of the deep lore reason is that row operations don't change the null space of your matrix, and your null space is going to be the linear combos of your columns that are equal to 0. So if there is a linear dependence going on in the columns of the ref, then it's represented in the null space, and then it carries over and blah, blah, blah. So your textbook goes through a more deeper explanation, but I always felt that just sort of a quick little example here really reveals what's going on. And note, the pivot columns have to be standard basis elements, and it's pretty easy to see that those are going to have to span the original. The fact that the span carries back to the original matrix is coming from the fact that null spaces are unaffected by row operations. And the linear independence has to also come from the fact that these are going to be standard basis elements, so any linear combo that zeroes them out has to be the trivial one, and that would hold true for these. So in particular here, we see this matrix, the first two columns would be a span for its base, for its column space. Let's do another example to really hammer it home. You get the ref, you find the pivot columns, which are 1 and 2. Those are going to be the ones that are going to be a basis for a column space. And now note, it's the original columns, the original ones from the matrix. The ref just tells you where they are. All right. Now we've figured out how to get a basis for the null space. It was just recontextualizing, solving for x equals 0. We now have a method for getting basis for column spaces. You just get the ref and get the column, pivot columns, and life is good. Let's focus now on the row space of a matrix. Ooh. Now, what is the row space? Well, as the name suggests, it's going to be the rows. That should be an m by n matrix, not an n by n. So always something. We'll do it live. All right. So we have m rows, and so if a1 to am are the rows of a matrix, its row space is its span of the rows. Right, column space is the span of the columns. Row space should be the span of the rows. Sounds good. Right, now, row operations will change our column space. They will move things around. They don't completely ruin them, but it does change some of the... Right, the set does get altered. It gets altered in a predictable way, but it gets altered. However, row operations never mess up your row space. Scaling a row, swapping a row, and scaling and adding a row to another, those are literally just linear combinations of rows. Right, you scale a row, you've scaled it. Right, you've introduced the scalar linear combo. Swapping rows, you've just moved them around. Right, that's a linear combo. Right, it's a boring one, you didn't do anything, but it's still a linear combo, and scaling and adding a row is literally a linear combo. So row operations do not change the row space. As such, whatever the rows of your reduced row echelon form matrix, they're still going to span the original space because the row operations do not affect the row space. Moreover, the non-zero rows of the ref have to be linearly independent. If they weren't, then there's some linear combo of the rows that equals one of the other rows, and that would allow you to eliminate one of the rows using row operations. but then we wouldn't be in reduced echelon form, right? If we are reduced, we are reduced. You can't delete an entire row, because if you could, you weren't in reduced echelon form. All right. Sweets. So, there you go. So finding a basis for the row space is pretty easy. Take a matrix, get its ref, non-zero rows are a basis. Now, note, the rows, right, are read horizontally, but the vectors, right, we'll write vertically. So just something to keep in mind. But there you go. So, 3 of the fundamental subspaces of a matrix. It's null space, column space, and row space. We now know how to get bases for these things. Ooh, very powerful. Right, and the power behind these things are going to be revealed as we go a little further. We're going to talk about dimension soon. That'll be next week, and we'll see some applications there, and having access to the basis of your column space and a null space is going to help us out there. And also getting a basis for your row space, pretty clean and easy to get it, and very useful. So note, if you have a subspace and you know it's a row space or a column space or a row space? What do I say? Row space, column space, and null space, right? If you have a subspace that you know is one of these things, you now know how to get a basis for it. Life is good. All right. So that concludes our quick rundown on bases. Let's now, in the next video, kind of loop things back around and go, well, we kind of already pointed out that polynomials look a lot like Rn, and let's make that a lot more formal now that we're pretty comfortable with what linear independence and bases have to be and how they have to behave.